All right, strange forces and a strange principle today as we delve into the Pauli exclusion principle. This is Physics X, Extraordinary Concepts in Physics. I am your quantum coordinator, Robert Nemiroff, and this is being brought to you from the beautiful downtown studios of Michigan Tech, where this is a upper-level physics course, but one that's heavy on concepts and light on math, where we encourage people from the world to check in and see what they think. You can find us in any number of places on iTunes or on the web at any of these addresses. So let's get to our strange world or universe with one of the famous questions I like to ask, keep people on their toes. So what keeps an electron from merging with a proton in a hydrogen atom? Why don't they just come together? One has positive charge, one has negative charge. Shouldn't they be friends? Is it electrostatic repulsion? Is it the Pauli exclusion principle? Possibly the title of this lecture. Is it the uncertainty principle, which we've had several lectures titled? Or is some bouncer involved? You be the judge. Think about it. Pause. Ask your friends. See which one your dog sniffs out as the best. All right, welcome back. The answer is, oh, it wasn't the title of the lecture. I fooled you. It's the uncertainty principle. So this is a strange one. Today is strange force day. We're all used to the fundamental forces, electricity, gravity. There's two other ones, the strong nuclear force, the weak nuclear force. Turns out the uncertainty principle can be involved in its own force. So if you had a small box, say, looked like this, and you were to put an object in there, say an electron, it would be happy. But let's say now you made the box smaller. You press on all three axes, as I tried to do. Then the electron will be trapped in the box, and you would know its delta x, say, and delta y and delta z even better. But according to the uncertainty principle, that means that the delta p must be larger. So the smaller the box, the larger the uncertainty in p, and so the more pressure it can bring about, because the uncertainty in p can be p. If you don't know what p is, it could be large. This is strange. So I am a physicist. I find this strange that the uncertainty principle can generate a force. And this force balances the electrostatic force between the proton and the electron and creates the bound state of a hydrogen atom, for instance. So hydrogen is held up by the uncertainty principle. At the end of this lecture, we'll get to a little bit more about squishing electrons and such. So, but let's keep going on the hit parade of strange questions. Why don't you fall through the floor? So many of you might have noticed that you have not fallen through the floor today. If you have, I apologize, and we're not related. Don't sue us. In other words, what is the primary reason that keeps two different atoms apart? Is it, back to the questions, standard ones, the electrostatic repulsion? Is it Pauli exclusion principle? Is it the uncertainty principle? Or do the atoms just don't like each other? Maybe they don't get along. So here we are now 20 minutes later after considering that. It turns out it's electrostatic repulsion. It's still not the title of this lecture. So we're still going. On the outside of all atoms, atoms have protons in the nucleus and they have electrons on the outside. And when you press these electrons against other electrons, they don't like to go together. They electrostatically repel. So the main reason, although it's a little bit more complicated than this, the main reason you don't fall through the floor and why your pen doesn't go through the paper and why you don't go through the chair is that it's electrostatic repulsion. The electrons are repelling each other. Okay? Still going. Why are atoms of higher elements fluffy? So hydrogen is the lowest atom in terms of number of protons in the nucleus. And you can have, I guess, any number of protons in the nucleus, but we only know of 100 or so. And carbon is 12, so we've got a bunch of those. But so the electrons, though, they don't all pile into the ground state like in hydrogen. Why is that? Is it electrostatic repulsion? Is it the Pauli exclusion principle? Is it on the uncertainty principle? Or is it deflufferizer available in stores? All right, it's now 4 days later, and the answer is the Pauli exclusion principle. You knew we had to get to it sometime. So as the quantum states fill up, electrons are kept further and further from the nucleus. It's balanced by the attractive electric force between the electron and the positively charged nucleus. So your body would be much denser if it wasn't for the Pauli exclusion principle. It keeps atoms fluffy. Most of everything is empty space. So there are slightly different reasons why things are empty space. So the Pauli exclusion principle conveniently collapsed as BEP says that two fermions, which are basically things that have, let's say, half spin or 3/2 spin in order of h bar, Planck's constant, they cannot occupy the same quantum state. They can't all be in the ground state. So electrons are fermions, and they can't all be in the ground state of hydrogen. Crudely, you might interpret this meaning that two fermions cannot occupy the same place at the same time with the same orientation in the same spin. This has been an observed fact for quite a while. It is derivable somewhat from mathematical discussions, which we'll just touch on, and that's something called the spin statistic theorem. Quantum mechanics, relativistic quantum mechanics. All right, so what force causes the Pauli exclusion principle? Is it the weak nuclear force? Is it the strong force, electromagnetic force, gravitation, or is it not known? So you can think about that. Is it one of those? Is it not known? So it's now several decades later, you're much older, wiser, you've read all the physics texts, and you now find out finally the answer is that it isn't really known. So we physicists pretend we know everything, but really we're just like everybody else. We take observed facts, we mathematize them, and we run with them. And we make clear predictions as to strengths of buildings and future positions of particles and uncertainties in particles. But something like the uncertainty principle seems to me, and I can only bring you up to my own level of misunderstanding, isn't known. So some hypothesize that the Pauli exclusion principle comes from extremely strong virtual particle exchange on very strong, very short distance scales. Some theorists, okay, so sometimes I'm anti-theorists. Theorists come up with ways of mathematizing things, and they will tell you that fermions have antisymmetric wave functions where you can say things like this minus that is equal to 0. But remember, whenever anything is 0, in my view, it really means that we've hit a realm of smallness where we don't understand. It's beyond physical understanding. So this math was created to explain known observations of the Pauli exclusion principle, and in my view cannot be used by itself to explore the limits and the cause of the Pauli exclusion principle. I'm unaware of a lot of research into that either. Okay, so as I said, there are lots of kinds of things called fermions that obey the Pauli exclusion principle, such as electrons, protons, and neutrons. However, there are bunches of particles that don't obey it. So it's not like the uncertainty principle, which gets everything, the all real particles. The Pauli exclusion principle applies to fermions. Bosons, such as photons, for instance, they don't obey it. Photons can all pile into the same place and time and state. And if electrons were all bosons, they would all be in the ground state. So to my eye, though, and this is another pontification on my part, electrons need not be completely fermions. They could be mostly fermions and could, in practice, have a small bosonic component. So every time they do an experiment, you don't prove that electrons are only fermions. You put a limit on the magnitude of the bosonic component and vice versa. Bosons might have a very, 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 very small fermionic component. The fermion and bosons are ideal states. We don't know. That means equivalent to something 0. We don't really can't go that far. So they do, however, this is one of the experiments that exist. You can start to cool, freeze nanokelvins, very cold, bunches of bosons and fermions. You can make boson-side condensate, which is lots of bosons in the same state. You can't make a fermion condensate. So experiments show here, clear experiments, that fermions repel by the Pauli exclusion principle as temperature drops, but bosons don't. This is interesting. So there are stars out in the universe. White dwarf stars are thought to be held up by what's called degenerate pressure, which is a way of saying the Pauli exclusion principle is involved. So they are all bound up in something called Fermi C, and they don't want to get into the same state, so it holds them up. So they're all in little boxes in a white dwarf, and gravity is pushing down. And so you can make them smaller because the white dwarf is very massive. It really pushes hard on the box. So you can know the positions of electrons in white dwarfs really well. But by confining them so, you get a lot of pressure. So when the pressure gets large enough, actually the electrons and the protons, they become neutrons. And the neutrons themselves, being fermions, don't want to be in the same state either. And so you press on them really hard and you get neutron degenerate pressure, which has 10 to the 20 times more, is 10 to the 20 times more rigid than diamonds. So actually here it looks a little bit like the uncertainty principle, but it's the Pauli exclusion principle, I believe, that holds these things up. So we've talked about the uncertainty principle being an intrinsic force and the Pauli exclusion principle being an intrinsic force, two strange forces that are on the edge of physics and hold up our world as we know it. And with that, I'll ask you to keep shorting away from your cat and talk to you next time.